NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, everybody. My name is Marc Razze from JPL's Office of Communications and Education, and I want to thank all of you for joining us for tonight's edition of the Von Karman Lecture Series. Tonight, we'll be talking about cameras and pictures, but being that this is JPL, of course, we'll be focusing on space cameras and pictures, and primarily those of Mars. From the first picture taken on the surface of Mars by the Viking 1 lander in 1976 to the incredible images we're seeing today from the Perseverance rover, it's evident that technology has come a long way in 40 plus years. Tonight, we'll take a look at the evolution of technologies that led us to the incredible images we're seeing tonight. Our co-host this evening is my friend and colleague, Brian White, also from the Office of Communications and Education. He'll be taking questions from the chat. Say hi, Brian.
Hi, Brian. Hi, Marc. Thanks for having me today. I want to remind everybody out there in the audience that this is their space program. So we want you to ask questions. We want you to be involved in this conversation. Our amazing social media team is going to take all these questions that you have in the chats. We're going to try to ask as many as we possibly can. Keep that curiosity going. Now, if you don't see the chat, go ahead and refresh your pages, and it should be right there. Looking forward to this talk tonight.
Thank you very much, Brian. So to take us on our journey tonight, we actually have two guests, both of whom are members of the Mars 2020 Project Imaging team. To start us off, please say hello to imaging scientist and Mastcam-Z Deputy Principal Investigator, Dr. Justin Maki. Hey, Justin, how's it going tonight?
Hi, how you doing? Great to be here.
Well, thank you so much for giving us your time tonight. So first of all, tell us a little bit about yourself and how you came to be at JPL.
Okay, well, I've been at JPL since 1997, and I design, develop, and operate imaging systems, mostly for Mars rovers, but also landers. And imaging system in this context includes the camera hardware, the software that controls the cameras, compresses the data and sends it to Earth and processes it on the ground. I came into the field as a physics undergraduate student at the University of Colorado in Boulder, where I worked at the Laboratory for Atmospheric and Space Physics for Larry Esposito and George Lawrence. I was working on the Cassini mission, and I was part of the hardware team that developed the ultraviolet imaging spectrograph, or UVIS. And then after that, I received my PhD at the University of Colorado. After that, I went to the University of Arizona at the Lunar and Planetary Lab, where I worked as a postdoc for Peter Smith on the Mars Pathfinder mission. And that was our first return to Mars since Viking. And then after that, I came to JPL in 1997.
Oh, that's a cool story. Was there what made you focus on imaging? Was there an image you saw at some point, or some particular moment, or something that kind of made you want to focus on imaging?
Well, yes, I've always been interested in physics and the physics of remote sensing, and certainly growing up, I saw the Voyager missions, those fantastic pictures returned from Voyager, but I also saw the Viking mission. And when I was a graduate student, I had a picture, printed photograph above my desk of the surface of Mars. And I always thought, that's pretty amazing that we can land landers on another surface of another planet, the surface of another world, and return images from it. And so that really was something I always had my eye on, as like, that would be really great to work on projects like that. And then I find myself doing it for my career. So it's great.
So then in your career, you've certainly seen and helped evolve the camera technologies used in a bunch of these missions. Can you give us something of like a historical review of these technologies and capabilities?
Sure. So as you mentioned in the opening, the surface of Mars, or Mars surface imaging, started with Viking. And so the first slide actually shows a picture of the Viking cameras that they flew. And this is really like old school technology. It's basically a scanning radiometer. And there's a picture in this slide that you can see that shows how it worked. It basically had a scanning mirror, and it would scan up and down and left to right and take pictures. It was actually quite heavy too. It weighed 17 pounds. So it was not what you would think of as a typical camera, but it took great pictures. And the next slide shows an image from Viking showing the fantastic pictures, the first pictures ever from the surface of Mars. It was really a historic mission. So that was the state of camera technology when I came into the field in 1997 and worked for Peter Smith. On the next slide, you can see what his camera basically was all about. This was actually kind of revolutionary. This was similar resolution to Viking, but much more compact and lighter. It had two eyes, sort of in that classic robot head look there you can see on the right. It had a full 360-degree range of motion, and it used CCDs. It was a typical framing. It was like a framing camera, like you would think of as a modern camera. And the next slide shows that it also was capable of taking fantastic pictures from the surface of Mars, again, at about the same resolution as Viking, which is about 3 times worse than the human vision, but still pretty good. And you can see that picture there. And one of the unique things about Mars Pathfinder, as shown on the next slide, is that we had a rover. And this was a technology demonstration of the Sojourner rover. And you can see there the little outline that it drove around. And we had to take pictures of it to find out where it was and how to command it, and just sort of learn about how to operate a robot on the surface of another planet. And it was a real popular mission. The next slide shows they even made a stamp out of some of the images that we did take. And you can see the Sojourner rover there sitting on the lander. And then the other new part about this technology is you can see in the next slide, the rover itself had cameras, and there was a picture of the lander that the rover was delivered on, which was kind of a view of things to come, so to speak, where we now had a new platform to put these cameras on. And then on the next slide, you can see that the Mars Exploration Rover mission, which was PI with Steve Squires, was a mission that a rover we built at JPL. And we kind of standardized sort of the modern rover imaging system. You can see the cameras there attached to the body, the cams or the hazard avoidance cameras. And then you can see the cameras up on the mast, so the nav cams and the pan cams. And the next slide shows that the cameras themselves advanced quite a bit in only a few years, where we had 4 cameras up on the mast this time, about the same resolution for the color cameras. But the next slide shows the real difference was that we were able to drive around. So this is a picture that we took of one of the landers. This is the Opportunity lander, where we drove away and we said goodbye to the lander and we kept on driving. And the next slide shows that we just kept driving and driving, and these cameras now could go really anywhere in the local vicinity. So that was a real advance. We proved that we could take these kinds of pictures and keep going and exploring. And then the next slide after that is a picture from the PanCam. This is now one of the first pictures where we had human eye resolution. And so it's color, and you could see we were driving up and down hills and things. And then in addition to that, the next slide shows we also carried a microscopic imager, which was capable of taking really close-up, high-resolution photos. This is about 30 microns per pixel. It's about the size of a stamp, actually smaller than that stamp I showed earlier. So we could take a robot arm and put it up to something and take high-resolution pictures of it. So then after that, the next mission, the MSL, Mars Science Laboratory Curiosity rover, much bigger rover. We kept some of the same camera technologies on that one, but we also upgraded them. And the next slide shows the next real advance in Mars surface imaging. On the next slide, built by the Malin Space Science Systems Group down in San Diego. Now, this is really the first time we had cameras that were really like a modern camera with focus mechanisms, color sensors, like the kind that you would get in your phones, your smartphones. But in addition, the resolution on these cameras, especially the one on the top right, was about 3 times better than the human vision. So, and then a little video camera down there in the panel C. So that was a real advancement. And you can see on the next slide, just the pictures that are still coming from this imaging system are really spectacular. High resolution photos. The next slide shows the kinds of photos of the geology that really advance our understanding of the planet. And so that was a real advancement. And in addition to that, the next slide shows the improvements that were made in kind of the hand lens imaging, the microscopic type imagers. This is the instrument PI was Ken Edgett down in San Diego, who works for the Malin group. Was also quite an advancement, had a focus mechanisms and just takes spectacular photos. And those cameras are still active. And one other thing that it brought to us in the next slide is one of the first real high-resolution Rover Selfies. And these are, you've probably seen these on the internet. They're popular, and they're actually a great way of documenting where the rover is in the mission. And here it is near one of its first places that it examined, Rock Nest. So those were the advancements. Then the InSight mission, which was just launched a few years ago. The next slide, we actually upgraded the cameras that we had at JPL to color. Now we're catching up on the engineering camera side of things, and we were able to take some fantastic photos on InSight. But the real next advancement came on the 2020 mission. So the next slide for that shows we now have 20 megapixel color imagers on the surface of Mars. So now these are cameras that would be comparable to something like if you're a real camera buff and you went to spent a lot of money on a camera in the store, you would get high resolution images, cameras like this. And then in addition to that, we also advanced the state of the art on the science cameras. And the next slide after that shows cameras with zoom lenses. So now we have the capability to zoom in on things from far away. So the next slide here shows, in addition, we had a whole bunch of other cameras, way too much to talk about now, but we have 23 cameras on the Perseverance mission, plus 2 on the helicopter. And we won't get into too much of that, but this is all documented. You can find it on the internet. And the next slide shows just a list of all the cameras we have. There's a lot of technology advancements that have allowed us to take pictures. And this next slide shows the rover and the cameras before we launched. We were testing them out at JPL. And then I always like to compare that with the next picture, which is one of the first pictures that we received from the surface of Mars, showing that everything made it there safely. This is a 20 megapixel Navcam image, single image of the whole rover. And then you remember down on underneath on the rover body, their HazCams take pictures. And the next slide shows a picture from the HazCams. So nice view of the terrain, full color, full 20 megapixel imaging. And then the next slide shows an example of what we can get from our zoom lens system, the Mastcam-Z system. Jim Bell's the PI on that. I'm the deputy PI on that. Jim Bell's at ASU. A collaboration with the Malin folks down in San Diego, again, advancing the technology. Fully zoomed photo of something like 2 kilometers away. So really capable imaging systems. And it's just been exciting to be a part of all this over the years.
Yeah, it's been crazy exciting to just look at these things. The pictures are stunning. But now we have video capabilities too, which is kind of new, right? Can you tell us a little bit about that?
We do have video capabilities, and it all kind of started, the modern era started with what I call time-lapse video, which is just what you think it is. It's a picture, some time goes by, and another picture. And so the first example of that is shown on the next slide, where the Sojourner rover was about to drive onto the surface, and we had this idea that if we maybe did some time-lapse imagery, we could make a video out of it, turn it into an animated GIF, and put it on the internet, which was this new thing at the time. These animated images. It's hard to believe that the internet was in its early stages in the 90s. But so we did this with these animations here, and we managed to capture it coming onto the surface. And as part of my work as a postdoc, I helped develop that technique and refine it. And the next slide shows kind of the full volume of work for that, which is basically little movies of Sojourner rovers scooting around on the surface. And these were very popular. And this really showed us that, wow, we could drive a rover around on Mars. Imaging systems are a really important part of that. And we were really developing the techniques and sort of, Mars Pathfinder, it's a great name. It really gave us the path on how to do these missions. So moving forward on the next real change in video, we did time lapse on MER, but the next change was for this video here, the MSL Marty instrument, again, Diego, which took video during descent. Again, it's a little faster than time lapse, 3.5 frames per second, but it's video, and it was our first view of what it's like to land on Mars. And then on the surface, we took the same capability with the Mastcam, and we managed to do videos of the scoop. And the next slide shows the scoop being shaken. The next slide, yeah, there you go, shows the scoop shaking some sand, and we were able to document a little bit of that. That was kind of it for MSL. The next big advance was Mars 2020. And the next slide, we have a system now that's designed to do high-speed video, and this is the EDL camera system. Specific task to do high-speed video during EDL. And so the next slide after this shows the parachute uplook camera. And this was the first time ever we were able to get video of a parachute deploying above the surface of another planet. And it was just spectacular. We were all very happy to see this video come back. It's a real great documentation to show what it's like. And the parachute team also really likes to see this as well for how their parachute performed. The next slide after this shows the view from the descent stage looking down at the rover. Now, if you watch, it happens pretty quickly, but the rover itself now is being lowered on the sky crane above the surface of Mars, and the rockets are firing and all the dust, and we were capturing all those dynamics as part of this video, showing the rover for the first time ever landing on the surface of Mars, and it was pretty spectacular. And then the sky crane cut away, and the next slide shows the view of the sky crane as seen from the rover. So now we're looking up, and this is what it was like. If you were on a rover and you were looking up, there's the sky crane pulling away, and you're being lowered down on the surface of Mars. And then if you watch carefully, it gets a little dusty, but then the sky crane itself will fly away after it cuts the cord and flies out of the field. You can watch it fly away. It looks like a kind of an alien spacecraft. It's about to happen right now. You keep watching, and it's really quick, and there it goes. And so now we're on Mars. And so we documented that with our video system. It's just amazing video, a real first. And then the last slide to talk about video is recently acquired images of the Mars helicopter. And if you listen carefully, we actually combine the video with audio, and you can hear the helicopter humming. So listen carefully. You might be able to hear. You might need headphones for this. So take a quick listen. So that's one of the first videos of an aircraft, a rotorcraft flying on the surface of another planet with sound. So this was the Mastcam-Z video system that I talked about earlier, along with the SuperCam microphone, which is brought by our colleagues in France, and it was just a fantastic collaboration. And so this is kind of the whirlwind tour of imaging systems on Mars as it stands right now.
Thank you, Justin. Those videos still give me goosebumps. They're just amazing. So this is probably a good opportunity to take some questions. So Brian, let's hop over to you and see how things are going out there.
So many great questions. I mean, it's hard to pick, but we're going to start with 1224 Chrising on YouTube. They actually wanted to know why you still use black and white cameras.
Well, that's a good question. So more recently with 2020, most of our cameras are color. We've done a lot of upgrades, as I talked about. There still are some black and white imagers, and typically the reason that we use black and white, those are much simpler systems, and sometimes all that's required is a measure of what we call luminance, which is basically brightness. Some of the navigation cameras, for example, on MSL are grayscale only. They're black and white. So it's a broadband filter, which captures all the visible range as is a single brightness value. And those are sometimes useful for machine vision, where color isn't as critical. But for science cameras, for example, particularly science cameras, science teams very interested in the color of things. And so that's why, for the most part, we've been mostly using color, especially on 2020.
Very cool. Something that kind of follows up with being on Mars and knowing what's there. Dennis on Facebook wants to know how you mitigate dust accumulation on the lens or the viewport.
Well, dust is an interesting problem on Mars. Mars is a very dusty place, really dusty. And so dust gets everywhere. It gets on everything. We do have on one of our calibration targets for Mastcam-Z, provided by our Danish colleagues in Denmark, they do have magnets strategically placed that sweep away the dust. Most of it's metallic. So when the dust lands on it, it gets swept away by the magnet. Those are called sweep magnets. But if you don't have those kinds of systems, and we don't have anything like that on the cameras, you just get dust. The good news is, obviously, it only accumulates a certain amount. Just like you think about your patio, you get a layer of dust, but you don't get a foot of dust. You just get this teeny layer because the wind keeps blowing it. And so that happens with our cameras too. We get a little dust, and then the wind blows it off. And it does reduce contrast a little bit, but it's not so much that we can't handle it. So we don't do anything in particular to get rid of the dust. The Viking camera actually had a CO2 gas jet to blow off the dust. And everybody that I talked to that worked on that mission, I did not work on that mission, but everyone that I talked to, they think they tested it out, but it wasn't a big deal. And so most of our cameras don't have any active dust rejection systems, except the ARM camera. Sorry, this is a long answer. We have covers on some of the cameras on the arm because we put the cameras so close to the surface that it gets really dusty down there. So we tend to have covers on those kinds of cameras.
It's a great answer. And the last question we'll ask for the moment is Nick on LinkedIn wants to know, what's the human eye resolution in megapixels?
Well, it's a great question. We don't measure the resolution in megapixels. Oh, you can, but then you need to know the size of the pixel and do some calculations and things. So what we instead measure the angular resolution, and that is basically an angle. And we typically do those in milliradians. You can convert those to degrees, and I don't want to try to do that in my head right now, but it's about 0.2 milliradians per pixel. Now, your eye doesn't have pixels, so it's a resolution test, and it can get pretty detailed. But basically, the people that market screens and everything, and they call it, you've heard about retina displays and things like that. That's essentially the resolution of your eye at some distance. And the number is 0.2 milliradians per resolution element in your eye. And those are like, for example, the PanCam from MER or the Mastcam 34 millimeter. And then with the 100 millimeter Mastcam on MSL and the cameras on 2020, we're now above human resolution eyes. We're taking pictures that are sharper than you would get if you were there. So that's the real advance. So that's why some of these pictures are just amazing in terms of resolution.
Very cool. Indeed. Thank you very much. So now, as much as the imaging and imagers have evolved over the years, so has how we produce and process the images. To talk more about that, let's welcome in our next guest, Mrs. Hallie Abarca, who is the Mars 2020 Image and Data Processing Operations Lead. Hi, Hallie. How are you tonight?
Hey, Mark. Thanks for having me tonight.
Of course. So, like we did with Justin, tell us a little bit about your background and how you got to JPL.
Yeah, I was definitely one of those kids who came to JPL's open house that they do every year. And when I was a ninth grade freshman in high school, I immediately went to the JPL open house, not knowing really what to expect, and then decided I was going to work on Mars when I grow up. And so I have actually stuck on that path and now work on Mars while I grow up. I was really fortunate to be able to go to Arizona State University. They have a really good program that's a joint planetary science engineering degree, Earth and space exploration, and got the opportunity to work for Marc Robinson, working on the Lunar Reconnaissance Orbiter cameras while all my 4 years that I was there. During that time, I got to do amazing things and actually work with image data products. And, being 17 in college, you don't really know what to expect. And so I've kind of grown up with image processing and doing terrain modeling and things like that for a long time now. And when I was getting ready to graduate, I was able to get an internship at JPL the summer before my last year, and got to do landing site analysis for upcoming missions like Mars 2020 and GEMS, which is now InSight. And that was a really amazing experience. And I knew I wanted it to be at JPL. And when somebody offered me a job to come work on Curiosity and MER doing image processing, I immediately said yes. And here I am almost 10 years later.
So that transition from college to JPL was pretty smooth, no doubt then, right?
Yeah, I was really fortunate. Not everybody definitely gets the opportunity to work on a flight project before coming to a NASA center. And so I was really fortunate to have that experience. So it was pretty natural to roll in to MER. And, while I've been here working up to Mars 2020, I've been privileged to work on image processing for MER and MSL, and actually led the image processing team on InSight Lander. I've been able to do uplink for the engineering cameras. I was fortunate to actually get to drive Opportunity Rover for a few years, which is something kind of just it still mind boggles me that I had the opportunity to do something like that. And have, worked on the 2020 robotic arm for a bit when we were doing testing leading up to launch. And then working on targeting software for Mars 2020, and then rolled into this. And it's really excited to get back into image processing. It's been really great.
Oh, that's so cool. So if you've been paying attention to the Mars websites from the public's point of view, we're getting just thousands and thousands of images from Perseverance and Ingenuity. How do you even begin to process all these raw images?
Yeah, it's kind of a crazy thing if you actually take a step back for a second. And how do we even get all of these images? So many things have to happen, and there's so many people involved to make all of this happen. I mean, we make a plan on the ground. We uplink a plan to the rover. The rover then takes these incredible images. The rover then at the end of the day has to send this data to one of the Mars orbiters, which we then have to get back through into the deep space network. And then that data has to get transferred to JPL. And then eventually it makes its way to our cloud computing, and we then process the data. And we have that last 5 minutes, and that's what the team that I'm on, that last 5 minutes is where we then try to get these images out as quickly as possible to the public. And that's been something that has taken many people to work on. We've had more than 50 people work on our image and data processing team in development over the last 6 years, and we have 10 people right now currently doing operations for this. So it's a huge effort. And when we're talking about thousands of images, we've actually released over 72,000 images as of today. And 33,000 of those are video from the Mastcam and the EDL cameras. So it's a really amazing amount of data that we've been able to process in such a short time on the surface of Mars.
And you've had like the panoramas too. Do they add any complexity to putting this all together?
Yeah, exactly. If you pull up graphic 40, something about, going back with the panoramas a little bit. So JPL actually, has created our own image processing software back in 66 is the first record that we've had Vicar around. And so we actually have been decades of heritage working on all of our image processing software here at JPL. And, some of my favorites I just wanted to pull up really quick are some of these two from MER, just to kind of show you the evolution of those mosaics. So we have these two MER panoramas from the navigation cameras right before we were dropping into Perseverance Valley on the top, and then right as we got into Perseverance Valley on the bottom. And then transitioning into MSL, it's going to look very similar for our navigation cameras on the top of this graphic. Again, here's a 5-frame mosaic of this outcrop back from 2015. And, it's definitely a little different than what we're seeing today. So just kind of transitioning into that, here's the MSL mosaic that Mail and Space Science Centers worked on after we had our global dust storm. So you can see that nice layer of dirt that Justin was referring to, or dust that Justin was referring to earlier, that's, coating all of our hardware. And then getting into the next frame, or next graphic we have here, we can actually see Insights Lander. So what was really cool about this is we actually had the same hardware for these cameras as MER and MSL, but now we have color imaging. And this is one of the things that Justin actually had worked on and was the lead for that, I believe. So here we have the before and after. So this is as we landed, and then 100 days later, you can again see that dust accumulation on the solar panels and on the deck of the lander. So what's really cool about how we actually made these panoramas is before, we have a mass that turns around and we can take a panorama, where this one we actually had on Insight a robotic arm on, and a camera on the robotic arm, and actually swung the robotic arm around taking these pictures. And so we were able to kind of piecemeal together and figure out where they all fit. And this is all command line based. So this isn't quite like Photoshop where you have this GUI interface. We're doing all of this processing with Unix command line tools. Just really, it's a really cool heritage to be part of. And so transitioning into Mars 2020 on the next graphic, I just kind of want to talk a little bit about how we actually put these panoramas together in a very simplified example. It's a little bit more complicated on our day-to-day basis. So this is actually the 6 frames that we have that make up this panorama that's on the bottom. And this is our panorama right when we landed. So I believe this is all 4, where we took these color panoramas. But if you look on top, we actually have, their grayscale images that we were talking about before. So if we go to the next slide, these actually are all separate red, green, blue exposures. So we actually then can turn these into color images. And so if you look at, on the raw images site, you'll see a lot of black and white images from early on in the mission, where we were actually in some of these cases taking these separate bands when we were still on our cruise flight software. So into the next graphic, we can then transition back, and now you can see the raw color if you just combine the RGB bands for these 6 frames. And that 6th frame, you can kind of slide it down. Now you can kind of see that we actually had 2 tiers when the eCam team acquired this panorama. And you can actually then see on the bottom where these all fit as we start putting this panoramas together. And a lot has to happen for it to get to look like this. If you notice that, there's different brightnesses, and you can actually see these are, fisheye lenses where you see the horizon actually curve on each one of these images. So there's a series of processing. So we make these into a panorama, as well as actually do brightness correction on all of these, radiometric calibration. And then going on to the next slide, you can see the seamless mosaics that we're able to do. What's really cool in Mars 2020 in terms of the changing software is we're actually generating all of these automatically now. It used to be before on previous missions that this would take a lot of time to get these beautiful seam corrected mosaics out. And, there's been a lot of focus on making sure that we could get these out faster. And that was one of the things that Mars 2020 wanted to focus on, is making sure, how do we do operations faster, and how do we get our data products out faster? And spending hours hand assembling these, really just wasn't an option anymore. So it's been really incredible to see this change over time. So going on to the next slide, just kind of wanted to talk about, we were talking about these high resolution images. So this is a single tile. So you can find this image out on the raw images site. So this is a single color tile that we acquired overlapping these original images. And what's really cool about these is they're actually stereo. So if you look on the next graphic, now you can actually see that there is actually a left and a right eye. And again, these are all out on the raw images website. You can go find these and you'll notice that, they all make stereo pairs. And what that means is basically, like we were talking about, we have a left and right eye, and then we put all of these frames together. And if you go to the next graphic, you can kind of start to see how we use these as stereo. So one of the most important things of our jobs is making sure we have terrains and all of the data products that the robotic operations team can use to actually drive this rover. And so now you can see this is a simulation of the actual, I think we've Solve 14 drive out onto one of the terrain meshes that our team produces. And on the lower right corner, you can basically see the images that it was taking during the drive. And, we were talking about earlier about the, machine vision liking these grayscale images. So this is a perfect example of, these are basically the auto images kicking off for visual odometry to do that machine vision.
Very, very cool. Very cool. Those are amazing.
With information.
Yeah, there's so much stuff. So Brian, let me cut to you and see if we have any questions for Hallie.
Oh, we have so many questions for Hallie that we won't get to all of them. But Aaron on LinkedIn asks, what kind of frequency band is used for transmitting the imaging data? And there's been a lot of questions about, compression and all of that in the transmission of back and forth, and how well you do that.
Oh gosh, that is a bit outside of my job scope, but Justin's been doing this a lot longer than I have, so might know the answer to that one.
Yeah, boy, that one's an interesting one. We use we have 2 ways of talking to the rovers. We have X-band communications, which are directly between Mars and Earth. I don't have the exact frequency off the top of my head, but then the main frequencies that we use are talking to orbiters. So we have comm links, and those are UHF frequencies, ultra high frequencies. And again, I don't know the exact frequencies, but it's X-band and UHF. Those are the 2 major bands that we use. Mostly UHF. For the images, it's mostly UHF.
Very cool. All that coming from the Deep Space Network. And the last one for now, and I know there's more that you want to get to. This is one of the most important questions we've been getting. Matt on Twitter wants to know how the rover selfies get taken when they don't see the arm.
Yeah, so it's fairly straightforward. Just like when you take a selfie, you see like, a piece of your arm and then it just kind of disappears off the image. What happens when we take these selfies on whether it's, Insight's lander, you also notice in that one we don't have a robotic arm or any of the rovers. We actually are taking the images with the robotic arm out at all different angles. So every time we move the robotic arm is actually where you're then filling in, the terrain below or, the rover hardware below. So you're never actually seeing the robotic arm in those images, and you're basically filling in all the holes around it. It's actually pretty cool. There's a lot that goes into that. And, the ones that are really cool on MER and 2020 is they're able to basically set up a point so they can actually take these images and not have any seams in them. The Insight lander was not quite so easy. So you'll start to see a lot of seams in there. And basically, the images from being taken at such different views, just kind of like if you did that with your phone and try to put those images together, you'll get a lot of different views and parallax around different items. So.
Cool. We'll get to more questions in a bit, but.
All right. In fact, Justin, let's bring you back into the conversation, but for Q&A. But before we go to the public for more, I have one. And that is, as compelling as these images are for the public and, of course, the science teams, are they also useful for mission planning?
They definitely are useful for mission planning. In fact, I talked a little bit about this idea that we have these rovers driving around, and that's really where we kind of demonstrated that imaging and imaging systems play a huge role in the operation of these vehicles. And so we talked a little bit about machine vision and what we do to make that possible, or what I do. It's part of my job. A lot of calibration of the cameras, knowing exactly how they're, it's not just a picture, but knowing how they're lined up relative to each other, the bore sight pointing, and the real detailed measurements of all the cameras and how they're all positioned relative to each other. And once we build that sort of database of camera positions, we then can take fairly accurate stereo data, which build these 3D trains that Hallie was showing. And then that's the world that we use to operate in. And so the rover drivers, the arm operators, the scientists that are targeting that rock over there and that rock over there, we know exactly how, or very close to the exact positions of where those rocks are. That's all enabling all of the additional instruments that we operate to point, laser beams at specific targets 7 meters away. And it's also used for by the rover itself, where it takes the pictures itself, uses the detailed machine vision calibration to figure out, how far away that rock is and then avoid it. So that's kind of the broad class of the ways we use those. But then it's just really, you see the picture from the surface of another planet, and everyone could look at the picture and say, yeah, that looks like a desert, or that's a canyon, or a hillside, or that's a rock, and you get that feeling that you're really there. It's an amazing experience to be able to take these pictures and for the first time see what it's like to be on the surface of another world. And that's what we do with the cameras. And so it really enables a lot of just operations and people's imaginations, just know what it's like.
Well, thank you for putting us there. Needless to say. So, Brian, do we have any questions for the two of them?
Yeah, I think Hallie's got one about, or Hallie has something about the next generation of that too, with Astro, correct?
Yeah, we have a new software on Mars 2020 called Astro, and I think we'll just let this video roll in the background. So one of the really cool things, when talking about mission planning is for all of our different team members, we have people all over the world. Right now, most of our teams are remote, as Justin and I are both working from home pretty much full time. And one of the really cool things is we can actually, on our web browser, have available to the entire team all of this information. So what's showing on right on the screen right now is the rover in one of its positions on Sol 28, I think that says. And this is actually the 3D reconstruction of the local data with the orbital data, and then the horizon actually used from the panorama that we acquired. So now you actually get a sense of what's around the rover. And, we were talking about, that sense of being there, but something that's really difficult is, an example is when I was a rover driver, you would get questions about like, oh, I want to, maybe put the robotic arm down on a rock. And that rock may be the size of like a small pebble or a large boulder. And it's really hard to just tell when an image, if you see an image of a rock, what that scale is. And now we have the ability to actually give to our science team tools that they can actually figure out what are the sizes of things, how far is it actually from the rover. That was another one of my favorites, is it's so hard to understand from an image how far something really is away unless you have that stereo data that Justin was mentioning. And now we're basically able to make this into a very user-friendly way for the entire science team to decide and figure out what their observations are. So one of the things right now, it's showing what the surface normals are for the terrain. So, and it's really going to help the targeting for the mission. Oh, sorry, Justin. Did you want to say?
Oh no, I was just going to add, if you're done, we had talked about this before. When we first started these rover missions, this is so advanced compared to what we had. And when we started on Mars Pathfinder, again, this was during the print era where we would print out, the photographs, and then people would stick Post-it notes on things like, okay, this is where we want to point the next observation, and so on. And this tool that Hallie worked on with Parker Abercrombie and folks at JPL is just such an advancement over what we even had 24 years ago. So it's just really incredible, the virtual worlds. And then it's also shared on the internet. So people can follow along using these great visualization tools. It's really quite amazing.
Yeah, it really is compelling to get that perspective for sure. So, Brian, any more? Go ahead.
I was going to say one thing that's actually really amazing, again, is we're actually giving the ability to the science team to actually kind of act like, knowledgeable scientist team members who can actually figure out and model where the rover is. So they can actually see what's actually playing right now is where the robotic arm is planned to be, and then basically plan their imaging and have all of this come together. And part of this is also to do this faster. Right now we're doing 7-day-a-week operations on Mars 2020. And, eventually we want to make it these shorter days, less amount of time. And, eventually hopefully get to, like maybe a 5 hours of a planning day. And now we can basically just streamline this entire process and have all of our teams really work together and integrate in a way that we haven't been able to before. I just think that's really, really cool.
Very cool indeed.
That's great. And what's amazing about the questions is a lot of times, though, I'll get these questions in and you will have both answered them right before we even get a chance to ask them. So that's wonderful right now. But we'll finish with 2 final questions. Sorry if your question didn't get asked today. Keep asking questions. Keep that curiosity coming. But Nick on LinkedIn asks, has your work on image processing led to any insights to future missions?
Well, I guess I can take that one. I think with each mission, we learn a little bit more about Mars, for one. So we're certainly learning about Mars itself, and it's certainly informing how to do things on the next mission. And you sort of saw that progression of learning better ways to build cameras, taking advantage of a lot of commercial technology to improve our imaging systems. And it dates all the way back, into the 60s, as Hallie mentioned. We started in the JPL started in the 60s, not myself, but folks before us, where the word pixel actually was first popularized by a group at JPL. So just understanding picture element, the needing to understand that, which led to a lot of detector development, which occurred at JPL, and now the imaging system. And now the commercial industry is really taken over with, smartphone cameras and video systems. And so we're always pushing pushing the edge of technology, developing it, and then there's sort of the synergistic relationship where maybe JPL will pioneer something that then industry takes and improves beyond what we could ever do. You're kind of seeing that happening now, actually, with self-driving cars. Some of the first self-driving cars were rovers, Mars rovers, and we have a lot of the robotics people coming in from the university systems, developing technologies at JPL. And now you see there are self-driving car companies all over the country. And so we learn a lot from every mission, and we learn from industry, and we keep advancing things as we move along.
Very cool.
Very.
That kind of sets us up for the last question, which is from Kia on LinkedIn. And this is for both of you. And what has helped you set yourself apart? Do you recommend how somebody could get to do the amazing things that you do at JPL?
Hallie, you want to go first?
Yeah, I'll go first. So one of the things that I always recommend is starting as early as possible to do something with your interests. If your interests are image processing, be pulling down raw images from all of these amazing missions. And, there's not even just Mars images. There's missions. We're releasing all of our data every, few months to the Planetary Data Archive. And we are actually coming up and we're going to deliver all of our data on August 20th that we process for the first 90 days. Jump in and actually get familiar with these data products. We even actually, we have Vicar is actually accessible to the public. You can Google it. It's on GitHub. Just really learning things. It's so much easier to come in and get a job if they don't have to train you from scratch, right? If you have an interest in image processing and you say, hey, I actually know a lot about this mission, whatever mission that is, and I understand what the tools are, you're so valuable to whatever that project is. And that you can really just, we're really trying to get all of this information out there. We have amateur scientists who are doing amazing work, making their own panoramas. It's such a gift that you can actually bring back to JPL or any NASA center or any mission to be able to provide something to them back.
And I'll just add, I think definitely pursue things that you're interested in. If you're a student out there and you're trying to figure out what to major in, follow your passions. I think that's really the secret in life. Do things that you enjoy doing. And I think there's so many interesting things out there that there's something for everyone. I would also advise to go to school, study hard. I'm a big proponent of education. Obviously, you need a lot of training to take on jobs like this. And so study hard. Listen to your teachers, listen to your parents, and just be curious about the world. There's so much out there, and with the internet these days, you can learn about all kinds of things, technology, science. I'm also a physics guy, so I recommend majoring in physics is a great thing. I highly recommend that. But any of the fundamental sciences, chemistry, or engineering, mathematics, there's just so much out there to learn. And so enjoy it and study hard, and you can get jobs like we have. There are just interesting jobs everywhere, all over the country and all over the world. And just learn about something and try to improve things and just enjoy it.
Education. It is indeed a never-ending adventure, isn't it? Well, that's about all the time we actually have tonight, folks. So I want to thank Brian, Hallie, Justin, our crew, of course, all of you out there for watching tonight. Stay safe, and we'll see you next month when we talk about perhaps our favorite solar system enigma, Jupiter. For now, good night, folks.